Oh yeah. Like yeah, every year you have four cycles all lined up on each other. You're just supposed to zero away from this is what we're doing. And like you haven't created anything until the last like 30 or 40 years. Like after the first year, you just start from somewhere. Yeah. Right before the start, the first year, you lose the movement. So you end up first year, our class, the last finals, and then get the finals.
I think we need to mute the volume. So volume.
Like you did at some part without oh yeah, I guess it's I think it's especially one of like I don't like the better way on your job. Oh yeah, I need like syndrome like you know.
Oh. Do you have a earphone? Do you have a earphone? No, you have got that? So in the class starts, you just check that whether the volume is being recorded or not. Because we made some changes, right? Yeah. It might so happen that the volume is not.
Okay, you ready? Great, let's get started. Sorry, a little late. Okay, so we're just about done with kind of all the intro stuff. Today we're going to talk about activation functions. So these are the things that are going to give us nonlinearities in our neural networks. And these are really important because if it was just stacks of linear models, we're just kind of composing a bunch of linear layers, we would just essentially be learning a matrix factorization of our problem from input to output. And people have been using those kinds of models for a long, long time. And while those are useful, again, it's just capturing linear relationships between things. So what makes neural network special is just this ability to really be expressive in terms of representing lots and lots of different nonlinear or large families of nonlinear functions. And we get that through these activation functions. So, yeah, remember what we're doing here. We're just building up Legos, and the main tool here is kind of a tiny detour here. So, it might have occurred to you the question, why on earth do we call these neural networks? So, they are based loosely on some understanding of how neurons, particularly in your brain, particularly in the neocortex, are organized. And this is not meant to be a neuroscience lesson, but just very briefly, a typical neuron looks something like this. It's got three main parts to it. There's the cell body, like any other cell body, but then it has these two other parts to it. So one is a long protrusion called the axon, and its job basically is to pass information from the cell body or whatever. So when like electrical potential collects or aggregates in the cell body, eventually that's going to trigger some sort of event that creates like a wave of electrical activity to travel down the axon and out to the ends of the axon that are attached to other neurons. And they're attached to other neurons at places on those other neurons called dendrites. And these are usually like large bushy protrusions that are, their main job is to kind of capture and integrate all of this electrical activity again to the cell body, and then when there's enough of a signal or of electrical potential aggregated there, then again something fires. There's this idea of firing, and again another traveling wave or pulse of electrical activity travels down that neuron's axon and goes out to the neuron it's connected to. This is a very stereotyped caricature of what's happening in neurons. And those of you who are neuroscientists or have studied neuroscience know it's way more complicated than this, but that's the basic idea. So how does this look like the neural networks, or how do neural networks look something like this? Well, you can think of our inputs as the signal that's traveling down the axon, and when that axon comes together with another neuron at that other neuron's dendrite, that connection is called a synapse, and you can think of that synapse as having some sort of ability to transfer that potential from the axon to the dendrite of the other cell, and that can be characterized by very simply as some sort of number that we'll call a weight, and that weight multiplied with the input is what is passed to the other neuron, and that's happening across all of the inputs that any particular neuron is getting. So it might have many inputs, and each one of those will be connected at a synapse. There will be a weight associated with that, and so we might think of what's happening in the cell body as taking all of that integrated or that transferred signal across all synapses and aggregating that together. This aggregation here represented by a very simple summation with some sort of bias term that's determined by the neuron itself. And then there's some way of determining how much signal there needs to be at the cell body to then create this output along this particular axon that will go and connect with other neurons. So the name activation actually comes from this neuroscience understanding. This activation function is like it's a function that decides how active or when does the axon become active for this particular neuron. And you'll recognize this looks a lot like what we've been doing, right? These are linear, it's some sort of linear model. for the integration of all the signal, and then there's some score of that, which at this layer we'll call the activation. And yeah, we've been doing neuroscience apparently. A very typical, in fact, in the early days of neural networks, this was all that was used for activation. A very typical activation function is this sigmoid. And we're going to see this over and over and over again. We've already seen it, when we were doing computation graphs. We were looking at these kinds of things, and this is simply some function that takes real numbers, so it takes signal along the real number line, and compresses it into this range between 0 and 1. So the larger the signal, like the closer this becomes to 1, and eventually asymptotes to 1 as x goes to infinity, and asymptotes to 0 as x goes to negative infinity. So this was really popular in the kind of the early days of doing neural networks because let's see, I had some note on that. Because this could be interpreted as like a firing rate, or like how much the axon was firing at any interval of time. From 0 to like its maximum firing rate. So anyway, that's the analogy. So now a warning: be careful with your brain analogies. What we are doing with neural networks really has zero to do with these, other than the fact that there's like a lot of things connected to each other, and that's also happening in the brain. Biological neurons. There's tons and tons of types of them. They're all doing interesting, different kinds of regulatory things. Some are primarily for signaling, others are primarily for regulating, up and down regulating, inhibiting even. I mean, there's all kinds of things going on with neurons. So our neurons, we're going to refer sometimes to like the nodes in these neural networks as neurons, but they're not neurons. They're not real neurons. They're just, for us, they're just kind of they're all the same, and they just all do very simple things like integrate all the signal coming into it, and then apply some nonlinear activation to it. Dendrites, because of the way that they work in biology, like they can do really, really complex nonlinear computations. Our whole neural network can do really complex nonlinear computations, but no like one connection is going to be able to do that, like one activation. We're going to use very simple nonlinearities in our activations so that we have a chance of actually I was going to say simulate, but of actually computing these things in the forward pass. Synapses themselves are very complex nonlinear dynamical systems. Actually, my PhD dissertation here at the University of Utah was on like how the weights of synapses change in response to electrical activity, how that regulates proteins, different types of proteins, different types of receptors in the membrane. It's really complicated. And and in this interpretation of the array code is like certainly not adequate for like understanding all of neuroscience. So anyways, that's all we're ever going to say about the connection to neuroscience. They're called neural networks for like a historical accident, and they have some, loose analogy, but we're not doing neuroscience. Okay, so there's all kinds of activation functions, all kinds of ways that you can apply nonlinearity after each linear layer. And here's a bunch of the ones that are most common. We just mentioned the sigmoid, so what you're seeing is the mathematical expression for each one, and then some graph of each one to get some idea of what it looks like, except for max out. So we were talking about sigmoid, takes the whole real line, compresses it between 0 and 1. And another important feature of it is that it's always increasing. So the derivative of this function, the sigmoid, is always positive, always increasing as you increase along the x-axis. Another activation function very similar to it, but with slightly different properties, is this hyperbolic tangent, or tanh, as sometimes call it. It's very similar, except that instead of compressing the real line between 0 and 1, it compresses it between -1 and 1. So it's symmetric about the x-axis. Has the same properties, though. It's always increasing, and it's asymptoting to 1 as x goes infinity, and to -1 as x goes to -infinity. So again, kind of giving you this nonlinearity, this compression into a finite range, but like in a symmetric way. Okay. Then there's Rayleigh or rectified linear units. We've talked about this a bunch. We've seen this a bunch already. This is just that max function we've been dealing with a bunch. It's like one of the most linear nonlinearities, right? Because for a huge portion of its domain, it is linear. And then, well, it's linear in both portions of its domain, I guess. This is also a line, very boring one, 0. And this one just being the identity. So it's very close to being linear, and yet it's not linear. And it has many, many desirable properties that we'll talk about today, but maybe a few undesirable ones. And to get around some of the undesirable ones, other types of like related activations were created. So another one is known as the Leaky Rayleigh. It's leaky because instead of it just being 0 in the range x is negative, it actually has this shallower slope. So instead of it being like the derivative here being 0, it has a small derivative. In this case it's 0.1. There's a lot of Leaky Rayleighs for any constant you put out there in front of the x, not just 0.1, but something less than 1, or between 0 and 1. And that, we'll talk about it more here in just a second, but the fact that you have some gradient, some derivative here that's non-zero is possibly useful when training neural networks, because you'll have a gradient. ALU, this is a exponential linear unit, so this is very similar. Again, it has the same property, but it has this exponential behavior when x is negative. So kind of like the Leaky Rayleigh, but it's a little more it's like a little more smooth, which may be good sometimes. And then there's this kind of weird one here, max out. What can you say about max out? What's max out doing? So there's clearly a max somewhere, as its name suggests, and as the expression suggests. But what's gone into there?
Takes the maximum length between two nodes.
Yeah. So what this is doing is you're basically learning two sets of weights and biases. Weights 1, bias 1, and weights 2, bias 2. You're learning both of them, and but at any time you only use the ones that are larger. So this is nonlinear because of the max. This max has nonlinear behavior, but it's just a max of 2 lines. So again, it's like it's another nonlinearity that's almost linear. But it is kind of weird because now you're keeping track of like 2 sets of weights rather than just 1. Yeah.
So the hyperparameters were that parameter that can be known.
So say again, like you're thinking about like this.
No. I mean the W1 and B1.
So these
hyperparameters.
These are not hyperparameters. These are
Neuron can be known.
no. These are the weights and biases. So these are like first class parameters rather than hyperparameters.
Okay.
Yeah. But things like this alpha and that 0.1 up there, you can think of those as hyperparameters. And I guess you could tune it. You could tune your model for those hyperparameters.
So here we train 2 models.
On max out?
Yeah.
Yep, max out basically is keeping track of like essentially two models. They both have the same architectures, like there's the same number of neurons in, neurons out. They're just two sets of weights and biasing that keep track of. So it's like you've got two sets of your models, but at every activation they kind of come together, and kind of compete with each other for who's ever larger. And if you think about that, what's happening is, whichever one's larger, the gradient, as you do back propagation, the gradient's going to come through the larger one, right? So only those weights are going to get updated. So there you go.
Which models will you pick?
That's the wrong question to ask in this class. So there's only one real answer to that, and it's don't pick sigmoid. That's the worst one. There's only ever empirical evidence here, and the empirical evidence suggests that you should mostly just use this. And we're gonna talk about all this right now. We're gonna go through each one of these and talk about pros and cons, and hopefully I'll convince you about this very empirical setting. But there is no proof that says, hey, use Leaky Rayleigh because of this. Like when you're just getting started with a problem, you'll usually start with kind of basic setups, and that basic setup will usually have all your activations being Rayleighs. But you might find that if you switch to a Leaky Rayleigh, that maybe you eke out some additional performance. It's usually never that beneficial over Rayleigh itself, but sometimes you can see that it is, and then you should use it because it's somehow better for that problem. So there's really no a priori way to look at a data set, look at your proposed neural network architecture and say, oh, I should be using max out here. And that should feel really unsatisfying for all of you diehard scientists and mathematicians especially. But it's just the nature of this. This is very, very empirical stuff at the moment. Okay, so let's start going through these. So sigmoids, like we've said a couple times now, takes your whole real number line and squashes it between 0 and 1. And like I said, this was if you look at all the older neural network papers, you only see sigmoids. This was the thing to do. And it's probably one of the reasons why not a lot of progress was made in the early days on these. I mean, probably the more important reason was that the computation that they had, the compute ability that they had back in the 80s and the 90s was not nearly what we have now. And that was probably the main reason. But these sigmoids made things hard, and we'll talk about why. So this is one of the main reasons right here. These saturating activations kill the gradients, right? So if I'm in this range right here, I think I have this. Hold on. I have this question asked right here. Yeah. So let's look at this. So let's think about back propagation. Okay. So back propagation. Remember, I've taken my upstream gradient from the loss to this point in my network, and then I want to multiply that with my local gradient. So let's say that my activation here is a sigmoid, and I'm multiplying whatever my upstream gradient is now with the gradient from the sigmoid. So what's my gradient look like when my signal is at -10? It's nearly 0, right? How about when it's 10? Again, it's really close to 0, right? But at 0, it's not 0. When x equals 0, it's not 0. So what that means is, if for some reason I'm already in my parameters are already set such that on the forward pass, the output I'm getting coming into this is, in these ranges where the sigmoid's already saturated, it's already kind of getting close to its asymptotes, and I have no gradient. So this gradient I'm going to pass to the next layer above me, or below me actually is the right way to say it. Below me is going to essentially be 0. So what that's saying is in this in this direction, or in all these directions, I have I want to take a step but it's going to be essentially 0, so I'm not going to move anywhere. So I'm not going to be doing any quote-unquote learning. The learning, right, is the movement through the loss surface trying to get to one of these local minima. So this is really bad. This is actually a property that we don't want to see unless we're sure we're already at a local minima. That's when we want the gradients to go to 0. We want to stop moving there. But if we're not close to there, we don't want it to artificially get there because we just aren't getting any feedback from our activation functions from our nonlinearities. Does that make sense? So this is what makes sigmoid a bad choice generally. Is that unless you're really fine-tuning things, it's really hard to keep out of these saturated regimes, which will stop your learning process before you get to a local minimum. Okay, so another possible problem is that this output here is always positive, right? So there's no negative output. So what does that mean? So the output's always positive. So as we go to the next layer, everything coming out of it, like it could have been both positive and negative when it was coming out of the linear part of the layer, but now we apply this nonlinearity, which makes everything positive. So what's going to happen? What can we say about the gradients there? Well, I don't know if you can say tons, but what that means is that either our gradients are going to be always positive or always negative. So we have to walk in these really kind of like not optimal ways. We can't if we're trying to go in some diagonal way that's got both positive and negative values in it, we can't do it. We're going to have to do this jumping around thing of like kind of passing it on one side and passing it on the other side and passing it on one side and passing it on the other side. When what we're trying to learn has got both sets of values. So that's not good. That slows down learning, that makes it less stable, and just makes it harder to do learning. So yeah, so we don't want this. So another bad thing about it, and finally, maybe the last bad thing about it, just having an exponential to compute is a bit expensive. How's an exponential function computed on your computer? This is a chance for computer scientists to shine, right? This is like computer science 101. Actually, I have no idea.
Is it a Taylor expansion?
Yeah, that's right. You take a Taylor expansion, you truncate it at so many terms, and so there's a bunch of multiplications and additions that have to happen there to make that work. And so that's just expensive. You just have a lot of flops there that you have to do. And if we can avoid that, I mean, we have very fast computers now, so it's maybe not that big of a deal. But you have to do this with all your neurons. If these networks have lots and lots of neurons, then you have to do this lots and lots and lots of times. Okay, so sigmoid's not a good choice. And in fact, if you use sigmoids in your final project, you'll probably get a 0. Because that means you didn't learn. You didn't learn how to prevent yourself from not learning. Yeah.
Move back.
Yes. This?
One other.
This.
Yeah. Thanks for the large gradient of the direction of all people are.
Say that again.
Why the all passes are just on particle are negative or negative.
Yeah, so the activation gives you is going to make them all positive. So they're all of the important thing there is they're all of one sign. So coming back from your gradient coming back from upstream is going to have a sign to it. It's going to make those either all positive, they're going to remain all positive, or they're going to change and be all negative. So what you have happening when you're working, what that means is that you're moving in like all negative or all positive types of directions. So you can't like walk in a diagonal direction. I mean, you can walk in a diagonal direction that is, say, like, that is all positives, but you can't walk in the right directions if the direction you need to go is up different sides. You're doing this kind of zigzagging path along the way, which, I mean, it can work, right? But it's just, like I said before, it's slow and it becomes unstable if you have like your running rate set wrong. You're doing a lot of jumping around where you want to be. Okay. So, next activation function, hyperbolic tangent or tang. This is almost just as bad as you can probably imagine. So it doesn't have the problem of not being zero-centered, because now this is now symmetric about the x-axis. Well, it's odd, but the values that y can take on are symmetric about the x-axis. But it still has these saturating regions, just like sigmoid. So tangents are also used a lot in these early papers. You can see there's a citation here where I'm not sure if this is, I can't remember if this is where it was first used or first successfully used, but tangent was introduced, at some point, and maybe it solved a little bit of computational problems, but like now you can get some negative values, but it still has a saturating problem. So you can stop learning too early just because you got your signal being too large, either in the positive or negative direction. So also, if you use tangents, you get a 0 on your final project.
Can we normalize the input data to solve the saturation problem?
Can you normalize the input data?
To solve the saturation problem.
Well, so in a single layer, yes. But as you go from layer to layer, you can't do that. There is a notion of doing this when we do. We'll talk about this when we do the convolution networks, called batch normalization, which will, like the job is to kind of center each batch, the outputs of each batch, like to make it more Gaussian, so it's centered and has like a more standardized standard deviation or variance, and that actually ends up being like a really nice regularization property, and it actually ends up like making each of the layers sort of independent of the ones downstream of it, which is a really nice property. And it has some parameters that are learned, and we'll talk about that. Like, so the answer is kind of like, yeah, you can kind of do it, but you can't really, like, if you don't have these learned normalization layers kind of in between, there's no way to do it a priori because of all the nonlinearities included. Like, you can't. I mean, when I say no way, like there is a way, but it would require you solving the neural network to do it. So you can't do it. You practically can't do it. But you're right. You can kind of think of it this way, and there are techniques for like initializing the weights and the biases so that you can get yourself started like in these regimes on average, so that there's learning at least early on. You don't want it to be that when you initialize your weights, actually everything is like you're already saturated, because then absolutely no learning will happen. But you can't guarantee that will continue as you iterate through the learning process. So that's a great question. Other questions on that? Yeah.
So why 0 center is nice?
Because your outputs can now take on negative values as well as positive values, right? So you avoid that like zigzagging problem that we were just looking at, because not everything is going to come out positive as you apply the activation to all your neurons.
So like that kind of curve would be like smoother.
Right. You could learn. Yeah. Your learning can walk in more than just like what are those called? Like ortho directions, but those like axis parallel directions. Other questions? Okay, so sigmoid, use or not use? Bad. Tangent, use or not use? Good. Oh, hey, look, Rayleigh. Rectified linear unit. Okay, so all of a sudden, this dumb thing actually starts to look kind of cool because, oh, one other thing we didn't mention about tangent. Tangent also requires you to compute exponentials as well. Okay, so yeah, this looks kind of dumb. There's a zero, you're zero all the way here, and then you're just this identity in the positive range. But it has some really great things going for it. One is it doesn't saturate. At least not like, at least just in this region. It's absolutely saturated in the negative region, but it has this whole place to play with here, where not only does it not saturate, it's absolutely linear. So it's and it's the identity function. So it's like the most trivial linear thing there is. So it's clearly going to always have a gradient in that whole region. It's super computationally efficient, right? Because all you have to do is a comparison with 0 for all the entries, and then you just the output is either 0 or the exact value that you're comparing with. So there's no need to transform it. There's no need to apply a function to it. You just return that address value. So that's great. And like, just practically, again, there's no real proof for this. Well, maybe there's a little bit of proof, but it just turns out that like because you're not saturating, you, at least in a large region of this, you tend to, with well chosen initializations, to converge way faster when using these kinds of models, because you're just getting, for the most part, you're getting good gradients all the way through your network, so that you can always be learning it. And again, like good gradients means you're getting signal to tell your model how to update its parameters, so you can walk down the loss function surface. And as funny as it seems, like how simple this is, this was not used, at least not used to like do something worthwhile until 2012. So Canches back in 1991. It took over 20 years to get to this Rayleigh. It seems trivial, but everything seems trivial in hindsight, right? Another like great property of this is that because this is like, this is the identity, it's basically linear. You're getting really linear behaviors when it's useful to be linear, and you're getting really non-linear behaviors when it's possibly useful not to be linear. And so it can like, the weights can be used, both those kind of properties can be used throughout your whole network to adjust what's going on. And we'll look at this a little bit later in this class when we look at like the output of these kind of activations. But it turns out that what you see. So remember the bias in this. So 1 second. The bias term gives you a chance to get away from so one thing you might be asking yourself is like, am I always like forced to just like, is everything forced to kind of be in this region? The answer is no, because of the bias term. The bias term allows you to like kind of adjust this point around so that it can respond even in negative ranges, right? And this is what makes this really useful, right? So you have your linear transformation, the W times X, and that's keeping 0 at 0. So your line or your hyperplane in higher dimensions is going through 0, but then your bias term is allowing you to move that around as the network finds useful. The bias term is also part of your parameters that you're learning that are being adjusted at every step, and that gives that allows this thing, for the most part, to to move this around and get itself in a decent range for most of your input.
That might have answered my question.
Okay.
I was gonna ask, wouldn't this have the same issue of stepping down in the same direction as like the Sigmoid?
Yeah, because it's having just
Because it would just be
positive output. It does have that. It does have that issue. It's similar to Sigmoid in that, and Tangent in that. Sigmoid in that respect. And this is why people have the leaky. Well, there's one reason why there's leaky in Rayleigh and A-Loo. But it turns out that it's not so bad because you can really fine tune when that happens with the bias term. That's also true for the Sigmoids and for the Sigmoid, like that same kind of thing. Like again, it doesn't mean that the output's not going to be positive. Just because you change it over here doesn't mean that the output's is not going to be positive. Like it's still going to be positive, but you can adjust it so at least what's happening is you're getting a 0 for a lot of the things, so there's no update, which is not a negative update, but it's like a negative update, but still keeping the possibility around being the next time in a dynamic range of the input. That's maybe kind of hand wavy, but that's different from the Sigmoid because Sigmoid is mapping everything in the positive range, not into 0 and the positive range. Okay. Yeah. Yep.
Yeah, I was gonna ask a similar question, but doesn't that kind of tell me where I'm thinking about is wrong? Kind of makes it seem like the real problem with Sigmoid is just that it's too tap it down, not that it can't go to 0. Or can't go to negative. Because this can go to negative and this does fine, right?
Yeah. So the real problem with Sigmoid and Tang is the saturating gradients. This also has saturated gradients, right? Massively saturated gradients for the entire negative range here. So it's also a problem here. However, there's a difference between there's a big difference between them because imagine the Sigmoid kind of being on here. There's a really finite range in which the Sigmoid has decent, the ability to provide you decent gradient. This has the entire half line here on which to give that to you. So it's way easier for the network to get itself into a parameter regime where you're getting lots of learning feedback from the gradients. So it's more subtle than what's said in the notes, which is I think what you're recognizing, what you're getting at. So yeah, this saturates, but the region again where it doesn't saturate is huge, and that allows it to be very dynamic. And this also has a problem of giving you positive output, but it's actually non-negative output. So the 0 obviously is a negative, but it allows you to at least get to 0 where nothing's happening, so that you can effectively it's easier to adjust that walk. It's that kind of zigzaggy walk. It's easier for that to be tuned to do a better job. I think we're actually, let's see. We're gonna play around something at the very end of this. We might be able to kind of explore some of these ideas. So let's remember that we have all these good questions about this and see if we can explore it in that. But yeah, let's see. I think I was saying something and then we had some questions and I can't remember everything I wanted to. Are there other questions on this? Yeah, go ahead.
Why can't we use just wide prefix line instead of this Sigmoid, so that we don't have
why not just use the identity?
Yeah.
So then you don't have a nonlinearity. So then you just have a linear model, right? That's why. You'd just be doing matrix factorization, and again, that's not the worst thing in the world. There's a whole great literature on that and how to optimize these kinds of problems, but you just have to have a linear model. So this is it's almost like that, right? So you're getting lots of benefits from that. like convergence is better because you're getting lots of feedback in the gradient, but you're allowing for some nonlinearity. And this nonlinearity is sort of easy to like work with. You just like, the things you don't want to pay attention to for a while, just kind of set them to 0 for a while and don't deal with them. And then all of a sudden they kind of come back into range and you know, in a big way because the dynamic range is so large. And it's sort of like turning on and off the ability to learn at each neuron. So it's totally hand wavy. Don't take that as like some sort of amazing proof of this, but that's the basics of it. Let's see, you next.
So why would the leaky Rayleigh be significantly better than the Rayleigh since it doesn't have the saturation problem, and it's also nonlinear?
Yeah, because it actually turns out that like just setting things to 0 is like is a good nonlinearity to deal with. It's computationally efficient, and it's sort of like there's just one behavior. There's like one nonlinear behavior you have to think about, and that is when things get set to 0. And the other one is just, you know, what usually happens is like they both perform pretty much the same. Just this will converge faster. That's all. Yeah. I don't know. That can be your final project, is exploring why Leaky Rayleigh and Rayleigh are basically the same. Give some good reasons for that.
All this gradient saturation, is that just the vanishing gradient problem?
Yep.
Okay.
Yep. Exactly. Yeah. Yeah. Another name for it: vanishing gradient. 0 gradients. These are all problems. When we have 0 gradient, we aren't learning. The only time that's good is when you're in a local minimum. Otherwise, it's bad.
So this nonlinearity, so without it, it would be just drawing a bunch of lines around things to classify them, or
Yeah, it would be very, very similar to like the linear classifier. It's just what you would have is you have more layers, which really means you're actually like, if you put the whole model together, what's happening is you're doing matrix factorization. So, you know, each layer looks like W. I mean, we'll just pick the bias for a second. It looks like W times X, right? So it's a composite. So like this is for the first layer. So for the second layer, it's going to be W2 times W1X, right? That's just That's just this matrix times this matrix times this, and then there'd be W3, W2, W1, right? That's what this composition is as you go from layer to layer to layer to layer. So it's you've chosen a way to factorize the linear operation going from the input all the way to the output by these different matrices. And you're just learning those different matrices. And there's a way better way to do that than just stochastic gradient descent, actually. There are nice techniques like block gradient descent and block coordinate descent, things like that. So, and they have like provable. Like as soon as you get in the linear world, then all the mathematicians are happy because it's like I can prove some theorems. But then it gets nonlinear, and then they all get sad. Can't prove any theorems. I have to linearize this around some equilibrium, and then I can be happy because I can prove a theorem because I'm back in linear world. And then I don't mean to be so cheeky, but it's just nonlinear phenomena are really hard to work with, and it's really hard to to prove like general theorems with them. That's why we don't have big general theorems around this stuff right now. Okay, try to move on, but happy to answer like probably one more question if you've got it.
It's not centered around 0.
What's that?
This is not centered around 0.
Yeah, so it has like we were just talking. Well, we were talking about this at some point here. It still has it's got non-negative output, so it still has a bit of a problem with the zigzagging thing again. You're right. Hey, look at that. Non-centered, zero-centered output. Okay, we talked all about this. Same picture, just a different activation. So, tons of signal at x equals 10, no signal at x equals minus 10, and at x equals 0, you get to choose what happens there. You can have it be 0 gradient, or you can have it be 1, or be gradient from the identity. You get to choose. It won't change anything. You'll never have x equals 0 anyways. Yeah, so this is pointing out this very thing. You can get into a regime where there will be no learning. But if you initialize correctly, if you initialize well, then you'll usually be able to learn. In fact, you'll always be able to learn, it turns out. So how would you want to initialize everything with radius so that you can make sure that you're like in your first iteration there's gradients you're learning. Whoops. Fat finger. Corrected that before you saw it. Yeah.
Randomize between -1 and 1.
Well, so you should statistically get like 0. If your input is like Gaussian, then you should expect to get your output to be, like the average output should also be, the expected output should be 0, right? That means that you should expect to see no learning on average, right? So, but I appreciate you actually going for it.
Yeah.
So if that's not right, what would be right? We want to get everything to just push a little bit over 0, right? So that there is some gradient. So we want to initialize the weights so that there's some positive bias of the output in that direction. So we want our weights to not be, so under the assumption that our data is normally distributed, then we want to set our biases so that those are not also, for instance, normally distributed, not symmetric about 0. We want there to be some bias, some skewness away from 0 in the positive direction, so that we expect, on average, to see positive output.
So is this bias only for the bias?
No, that's an unfortunate conflation with bias. This is like positive bias to the distribution of weights, meaning like it's shifted away from 0 in the positive direction. Yeah, good question. There's actually more precise ways to think about this given your input data. We'll talk a little bit about these for certain networks. Okay, good. Hopefully you're getting some feeling for activation functions. So, Leaky Rayleigh, we've basically talked about this already. Somebody's already brought this up. It has all the benefits of the Rayleigh, and it has maybe one additional benefit, which is you never have a 0 gradient. It's non-zero everywhere, and so you've always got signal. This is, of course, so this is chosen so that the gradients here are smaller, like than the matching gradient or the corresponding gradient for the negative value. So why is that? Why did we choose a different slope here rather than just like 1? Yeah, we still need to be nonlinear somehow, right? So you have to have some nonlinearity. So this is why there's this bend. Why is this smaller than 1? Why isn't it like it's greater than 1? So like the slope would be like this. What's that?
We think the signal is negative, so it's not active in neuron.
Yeah. Yeah, maybe. It's really just that you want this to share some of the properties that we're good about Rayleigh, which is like everything is pretty small over here, so it's like easy to deal with the nonlinearity as at the population level. Like nonlinearities are always going to create something that's small. It's just that this has this additional, I don't know, could be a good property that that there's also a gradient there. Like I said, it doesn't really give you much benefit usually. So and you have to actually do this computation, right? So technically it's slightly slower than using the Rayleigh because you have to multiply your input by whatever it is, 0.01 or whatever, and not just place a 0 there. But you know, most computers it's essentially the same. So yeah, so it doesn't die, but honestly, that doesn't really help you much. And I would love for somebody to do a great final project like all about these kinds of things and explore this in great detail across lots of interesting data sets and show that that's actually the case. Or maybe you'll show that like you prove some awesome theorem and you publish a paper and you become famous. That would be awesome. Don't forget about me if you become famous. I taught you about this the first time. Yeah. So there are different ways of thinking about this. You can think of alpha as a hyperparameter, like we talked about before. You can even think about it as being a parameter to be learned. So you could backprop through your parameter alpha here and learn that at every single activation. So this would be like an additional weight at every activation. You could learn it. It could be part of your computation graph. Again, awesome final project. Someone should go through all these things and show that it doesn't matter. Or it does matter and it becomes famous. Either way, it seems like a win-win to me. Okay. And then finally, you have these exponential linear units. Really very similar. It's just you have this sort of exponentially dying behavior going to asymptoting to -1. So this this is different from the Leaky Rayleigh because the Leaky Rayleigh is going to go out to -infinity as x goes to -infinity. The exponential is going to asymptote. Right, because this is the exponential, so you think of it as it looks like this going through 1, but you subtract 1, so now it's going through 0, and it's instead of asymptoting at y equals 0, it's asymptoting at y equals -1. And you can adjust that too with this parameter, so you can have that go to whatever you want. But I promise you it doesn't matter much, and it gives you an extra hyperparameter to think about, and you have to compute this exponential, which is definitely slower, even though maybe you don't experience it as being slower. Usually like the rate limiting steps in like serious neural networks, like with images, especially like with big images, is like the whole transfer of images into like from CPU memory into GPU memory, and then reading that out into your network. Those are the rate limiting steps, not necessarily calculation of these activations. So it really usually don't matter which one you choose. You kind of get the same like basic time to train. But it is computationally more expensive. And look at that, ACE didn't appear until 2015. Oh, like this is a new field.
Yeah, why do we have the asterisk?
Why do we have what?
The asterisk. So the brown line.
Oh, why do we have those?
Yeah. We just subtract by 1, and how is it different from the regular one?
This is like, let's see. Yeah, so like you're asking like, like what is this S rated? That's what you're saying. Yeah. Let's see, what is this called? That probably is something like shifted. It's just taking your Rayleigh and it's just shifting it down, and in this case to the left of it. I don't have a slide for this, so I actually don't know off the top of my head what this S Rayleigh is, and I promise you it's not any better than Rayleigh. But it would give you some negative values for a little while. Yep. Okay.
Sorry.
Yeah.
One question on that.
Yep.
So could you kind of give us an example of if we were just to compare this S Rayleigh to the Rayleigh at a specific point in that graph? What is it going to do to that neuron?
I mean, you can see it right here, right? So this has a slightly larger dynamic range, and it is instead of having 0 as its output, I mean, it still has 0 gradients in this large range here, but instead of having 0 as its output, it has -1 as an output here. So there's negative values, so it doesn't have that, like, everything's non-negative problem. That's all. So it's going to behave pretty much the same, just kind of gives you, like, maybe a little more blades on the Swiss Army knife to kind of play with, but it won't matter.
So the neuron will always only fire if it's positive.
No. There's no firing here, right? This is just like whatever is the aggregated input coming into this neuron. It's going to fall between minus infinity and infinity, and the activation, like the nonlinear you're applying to it, is this, is now this brown line, so it's going to be, -1 from whatever this value is, all the way back, and then it's going to be the identity all the way forward. So, I guess that's a -1 because this is the identity here. That's -1 right there. So, I don't know, like it just behaves slightly differently. Like there's now this range from -1 to 0 where you have a negative value as part, like you've included this as part of the identity, and then everything's just -1 all the way here. But again, you'd have like saturating or vanishing gradients at 0 gradients in this range, so there would be no learning when you're there. But you'd have a negative value for the activation, so might be some benefit. But it won't help. It won't change things. I promise. Other questions about that? Oh yeah.
So for this graph, like, does that mean the bias can also change?
Yep.
So you kind of go like a
Yeah, the bias can shift things around, exactly. That's like the main reason for the bias is to give you that kind of ability to shift things around. Max out. Yeah, so max out's kind of interesting because this does generalize Rayleigh and Leaky Rayleigh, right? Like in the sense that if this weight and this bias is 0, this is a 0. So that looks like Rayleigh. If this is a 0 and this is 0.01 like we saw before, that's part of the family of Leaky Rayleigh. So it does, you can learn those activations along the way. You're always linear, no matter like whatever region you're in, you're always linear, so that's nice. So that you're never having saturating gradients. But like this says right here, you are getting twice as many parameters to keep track of. And when you have 25 million parameters, maybe 50 million parameters is undesirable. If you have 1,000 parameters, maybe 2,000 parameters doesn't matter. But, when these things start to get big, this just starts to be like kind of unwieldy, and it doesn't really matter. You just do it, and it will usually it'll be just fine. Okay, so the advice: use Rayleigh. And yeah, you're gonna have to tune your learning rates. That's true for all of these. You can try all these other ones out: Leaky Rayleigh, Max out, Rayleigh, anything S Rayleigh. Like try them all out if you'd like throughout this class. You should explore. You should convince yourself of what works and what doesn't work in these things. Don't just take my word for it. But so try these things out. So great, try them out, and just see for yourself that it won't be any different from Rayleigh. Try Tanch out. That won't do much. And if you use Sigmoid, you get a 0. Actually, if you use Tanch, you get a 0 too. So just be warned. Sometimes I will say that sometimes there's only one time when you should use Tanch, and that is when you have to compress something into a finite range. This is a decent activation to use, but you will have vanishing gradients, I promise. Okay, so fully connected neural networks. So these are the simplest neural networks to think about. They're the ones that we've been kind of anticipating for a long time here. So remember, we've been talking about our score functions as these simple linear functions. There's always a possibility for a bias term. Sometimes these get dropped just for simplicity. But if you don't see it there, just imagine that there is a bias term sometimes. Okay, so now if I'm using Rayleigh and I have a 2-layer network, then what does this look like? Well, this looks like I first do my first linear function on the first layer, the weights from the first layer, and then I apply my regular activation. So that's just this max between 0, or maybe 100 by 3072, depending on how you do your matrix multiplication. But right, it's going to be a matrix of that size. It's going to be projecting from 3072 dimensions down to 100. There's an H used there because that's a hidden layer. See that notation a lot. And then I output to my score. So I have another matrix here. It's going to be of size 10 by 100. If I have column matrix or column vectors, and that's going to be my score. So I solve that notion of the score function here, right? We're still using scores. These scores are still going to go into a loss function. That's how we're going to optimize our network. But now, instead of just having linear functions, I'm now just composing linear functions and putting activations in between them. And now all of a sudden I have nonlinear behavior. And somehow, this learns the difference between cats and dogs. See? This is that same picture we were seeing before with just a linear score function, but now these are the weights from this first matrix, but now in this now when I learned, I have 2 layers here, and those maybe look a little bit better than the ones before, but they don't look that different. I can keep doing this, right? I just keep using Rayleigh. I just keep doing these compositions, and I take my output from the last layer and just apply Rayleigh, and then multiply by the next set of parameters. I can just keep doing this. And this is how I get a fully connected feed-forward neural network.
You have different activation functions at
Yeah.
different layers.
You could.
Why would you want to do
You
that?
wouldn't. There's no reason. Except if you need to put your final output into a certain range. Like so there's a kind of activation called like Softmax. We talked about Softmax, right? This is part of a particular loss function when we were doing cross entropy. Like that's an activation. That's like a nonlinear transformation, and it's different from Rayleigh. So like usually your activations of your final layers are often different than what you would use for the whole thing, typically Rayleigh, because you need to get you need the output to be in some sort of form, and so like Softmax is a good example. It takes your outputs and puts them turns those into a probability distribution. But maybe instead of that, you need everything to be like in a hypercube between -1 and 1 or something like that. So you use Tanch or something else that does that. Yeah. Good question. Yeah.
Wait, so like should we use different activation functions on different layers, or shouldn't?
No, that's the same question I just asked, and I would say no. In general, the answer is no, although I'm sure there are situations where the answer is yes, but in general, the answer is no. Except for the last layer, when you need to prepare for the loss function.
So is that because like we have no idea about each of those?
It's really like an Occam's razor principle. Like, there are a lot of choices here, and you don't know a priori like what you should choose. So choose something that usually works and keep it simple. So that means Rayleigh everywhere.
Like a campaign manager over there, you know?
Yeah. Rayleigh for president. Okay, so let's see, how much time do I have here? 10 minutes. Okay, so yeah, these are actually pretty simple to do. This is an implementation of the training of a full 2-layer neural network in Python. So this is doing like 2,000 iterations here. You just have some random. There's some choice of dimensions. There's some random data and labels chosen. You randomize your initial weights. Notice that they use the sigmoid, so they got a 0. Although actually there's sigmoids in your homework right now, so in these initial homeworks if there's sigmoids there, do them. Because if you don't do them, you will get a 0. That would be weird. But I'm talking about your final project. And your final project is 0. You know, so there's just, so like this is what, so this is your initial set of weights times your initial input. You apply this activation function of sigmoid to get you your hidden output. You get your output for the next layer here. There's no biases in this. If there were biases, you'd be adding a bias term here and a bias term here. And then this is like a regression problem. There's just a squared loss here. It's like an L2 loss between what our output from our simple network is and the actual labels. And then this is just computing the gradients. This is the back propagation from the end to the beginning. You can see like this is our L2 output, so like this is that gradient of the L2 output. And so forth. And then this is choosing a learning rate of 10 to the minus 4 and using the gradients of the two weights to update your weights. And you just keep doing this, and you are training neural networks. You can put it on your resume, and now your value's gone up like tenfold. But all you really done is like stuff that was being done in the 80s that people were embarrassed for a couple of decades to put on their resume. But yeah, it's pretty simple. Like what we're doing is really simple. At least like the basic notions are really simple.
I've noticed that you basically just pick fixed like training cycles. Is that typical, or are there other things that are sometimes going in?
What do you mean by fixed?
Like 2,000, right? Like it's 2,000 times.
Yeah, we'll get into the training dynamics and how you might think about
Everything.
Yeah, so like usually you pick a max number of iterations you're going to do,
Okay.
and then there are usually criteria for stopping early.
Okay.
Yeah. Yep.
I've noticed that as you're going through like the different layers, you're choosing as you're reducing the dimensionalities. How do you determine how the dimensionality should reduce as you're going through those different layers?
So the architecture itself, the choice of the number of dimensions is another hyperparameter, right? So everything's a hyperparameter here, except for the weights and the biases. Literally everything else is a hyperparameter. So those are all things that you could tune, using cross-validation. You will go mad doing it because there's so many hyperparameters, right? And there are like tools for doing this, but you might not have enough money to spend on GPU instances in the cloud to go through all the things you want to do. So there are definitely hyperparameter optimization is a great research area that people are thinking about, but there's again no like surefire way to get to the optimal architecture and things like that, with a limited number of resources, including time. But yeah, there are hyperparameters. Yep.
It seems that there are some algorithms now that will try and select the best architecture for you. Is there any, do you have an opinion on that, like compared to?
I don't know tons about them. I mean, there are now ways of kind of back propagating through the choice of the architecture. I don't know of any situation where it made a really big difference. Usually what this is doing is eking out a tiny bit of additional accuracy or something on the classification problem over your standard kind of hyperparameter optimization of a fixed architecture for example. So there might be a time when that becomes really powerful and we can use it a lot, but it really is computationally intensive and requires a lot of because every time you choose one of these hyperparameter sets of hyperparameters, you're essentially having to train that whole network through to convergence. And that's in the toy problems that we do in the homework and things like that, that's not a problem. But when you're using serious data sets, that's a huge problem. These things might require a whole bunch of GPUs and many GPU hours or days to converge, right? So you don't have the luxury of just waiting around for 10 years to get the optimum response back. And that optimum is usually a tiny fraction above where you found in a short amount of time. Like a serious Pareto principle thing happening here where you can get a long ways with a lot of heuristics and be fairly close to optimal even though you're not necessarily optimal. But that isn't me saying like you should never look into those or try those. Like it's just a trade-off for for resources. Okay, yeah. So you're doing this in the homework. Yes. Hopefully you've gotten to that. Don't leave it till last week. I think there's actually quite a bit of homework in this first one, so please don't leave it till last week, because then your life will be bad, and then you'll be mad at me. I don't like that. Okay. Oh yeah, just some ways of talking about these things. So when we so this is a 2-layer network. So the layers, there are literally 3 layers here, right? 1, 2, 3. But the input's not a layer. The input's just the input. So there's your hidden layer and your output layer. So the layers refer to like these weights, right? So like this, this set of weights gives you your first layer. This set of weights gives you your second layer, and you just kind of continue that on. So your first layer, your second layer, and your third layer. So this is how we talk about the layers. And the output layers are called heads of the networks, and we'll typically draw these on their sides like this because it's just easier to draw. But if you're going to draw them vertically, the input goes at the bottom and the heads go at the top. If you do it the other way, everybody will know you're a noob. You don't want that. So heads are at the top, feet at the bottom. We don't call those feet, but the input's at the bottom. But if you rise by neural networks like this, where I'm allowed to adjust the size of this hidden layer is so mathematically this is dense in our continuous functions on a finite range. What this means is I can approximate basically any function of interest, any function I might ever care about, by a particular choice of neural network just of this size. So these are known as universal approximators. They're super simple, but there's always a neural network, with a fixed input and fixed output. There's always a neural network that can get as close to the function that I really care about, or the function that actually generates the data, or whatever. With it, so I pick some sort of tolerance, some sort of error that I'm allowing there to be made. I can always find a neural network. It's basically proportional to the number of wiggles in the function you're trying to learn. So every kind of up and down movement along the way it's trying to make. And that means if your function is really wiggly, you need a lot of hidden neurons to the point where it might not even be practical, even on all the awesome computation we have right now, or all the awesome compute we have right now, and servers and GPUs and things like that. We might not be able to hold all that in memory or efficiently train it. So while they are universal approximators, we aren't guaranteed to find ourselves the approximating function to the tolerance that we want and still be able to compute it. And the important thing here to note, and we'll just kind of leave it here at this idea, is that we overcome this part of this aspect, or this constraint of the universal approximation theorem through depth. So basically through taking all the neurons that needed here and distributing them out through more and more layers. And the more layers we have, the more opportunity we have to learn kind of general and more abstracted features, building those features up to a final output layer. So we need far less neurons overall to kind of get the same level of approximation. So while this theorem applies for just networks of a single hidden layer, so two-layer networks, we use networks of far greater depth to overcome kind of the unbounded need to grow that hidden layer. Anyways, we'll stop right there. Yeah, see you on Tuesday.
now, the gradient is actually this one.
On tangent, I'm not sure if you're saying. Yeah, it's that the output is all positive.
I'm kind of scared myself.
So you are always starting from a
Why did you stop recording? Like that?
you're always in one of these cones in this.
Stop the recording?
The
No. What happened?
so like everything's always everything's always in these positive cones, or if you somehow have a negative.
No, that's not what to consider.
So if you need to learn something that's down in here, you're gonna have a hard time getting there because you can't make movements in these directions. You have to make movements in the like in these cone like.
What are the axis?
These are axes of our weights.
Weights.
Well, it's our output. So it's not our weight. Sorry, this is actually the input to our next layer, right? So this is like, and there's just two. So like maybe call this, f of x1, or maybe I should do it that way. W x1.
So the output here is always
f of w x2.
No.
It's also wrong to do this. This is like, so this is all.
So you mean
What I mean is like the whole thing.
outside.
More.
So
That's what it is.
number of weights.
Yeah, which is also putting it back here, right? Because these are always entry points. Yeah, so it's just that like your data is always sitting up here. So like, if you need to get like data